Hello, welcome to another edition of James and Chris Science videos, where today we're going to be looking at pressure. Throughout this video, I'm going to look at the equation for pressure, we're going to give a definition for pressure, I'm going to give you some worked examples of how to answer questions on pressure, and there's a practical for you to try at home near the end of the video if you would like, with parental permission. Now, in order to start this, every physics teacher in the world, I think, uses the question of what would hurt more and what would exert more pressure, an elephant or a woman in stiletto heels. It's a standard question. I've seen it so many times. But let's go through this and let's try and answer that question. If an elephant stood on your foot and a woman stood on your foot in a stiletto heel, which one would hurt more and which one would apply the most pressure onto your foot? So to understand this, we need to first of all look at the definition for pressure. And the definition for pressure is that pressure is an amount of force applied over an area. So, little simple example, if I push down on my hand with my finger, all the force that I'm pushing down with is spread out over the tip of my finger and it's concentrated in that area. If I put my palm down and push down, then the pressure is different. The force that I'm pushing down with is spread out over a bigger area. So the pressure put on my hand is different. Now you can see this in action if I had a tray of sand and I tried to put my finger through the sand and then I tried to put my hand through the sand. It's much harder to put my hand through the sand because the pressure is spread out over that area. Now we're going to apply that to my question about the elephant and the stiletto, and we're going to start off with the elephant. Now, we're going to look at that equation. We're going to use that equation to work this out. And the equation is, again, pressure equals force divided by area. You're going to need to know that equation, so it's worth just repeating it until you get it. Now, if you actually look at the units and the words, it makes sense with what I said before. Pressure equals force divided by area. And I said that pressure was the force that I pushed down with spread out over an area. The wording's very similar. I've put the units in. Now there's lots of different units for pressure. You could use newtons per centimetre squared, which is what I've used. You could use newtons per metre squared, which would be the same as a Pascal. You could use pounds per square inch. America tend to use that quite a lot. You could use bars when approaching pressure in air. But in our syllabus, in the ISEB syllabus and the Key Stage 3 syllabus, the unit that they use in the questions is newton per centimetre squared. So throughout this video, that's what we're going to use, newtons per centimetre squared. We've looked over the internet and I found out that the average mass of an elephant, and I've used African elephants rather than Asian elephants to give me a bigger number, but the average mass of an African elephant is 6,000 kilograms. Now, if you remember back to the lesson that we did about gravity, if the mass of the elephant is 6,000 kilograms, and we know that the gravitational field strength of the Earth pulls down each kilogram by 10 newtons, that means that an elephant with a mass of 6,000 kilograms is going to have a weight of 60,000 newtons. Each kilogram pulled down by 10 newtons. There's 6,000 of them. So the weight of the elephant is 60,000 newtons. And that is a force. It's measured in newtons. It's the pull of gravity on that elephant. So I've got my first figure that I need for my equation. I've got my force. I then researched and it says that the average area of an elephant's foot is 1,800 centimetres squared. That is about 0.18 metres squared. Now, of course, elephants have 4 feet. So we need to times that by 4, and the overall area of elephant's feet is 7,200 centimetres squared. So there's the second part of my equation. I've got the first part, the 60,000 newtons, and I've got my second part, which is the 7,200 centimetres squared. So if I put that in, and I work this out on my calculator, 60,000 minus 7,200 would give me a reading of 8.3 newtons per centimetre. That means every centimetre of the elephant's foot is pushing down on the ground with a force of 8.3 newtons. That's very useful for an elephant because they're heavy. They need to spread their weight out. If they didn't, they would sink through ground. Any kind of soft ground, they would go really deep into it. So they need to be able to spread that weight. Now, your turn. I'm going to give you some information for a stiletto heel, and I'd like you to work out what the pressure of the stiletto heel is using exactly the same method that I've just showed you. I'm going to give you a force, I'm going to give you an area, and you're going to be able to work that out on a calculator. So I was thinking, if they were going to tread on my toe, who would I want treading on my toe? So I've tried to choose someone fairly light. I tried to choose someone that hopefully would be very nice about it and apologetic, and maybe even knight me. So I've chosen Queen Elizabeth II. According to Google, Queen Elizabeth II has a mass of 55 kilograms. Whether that's true or not, I don't know, but I'm going with it. So if she has a mass of 55 kilograms, that would make her weight 550 newtons. Remember, each kilogram is pulled by 10, so 55 times 10 would give me 550 newtons. That is the force that Queen Elizabeth puts onto the ground. A stiletto heel. Now, I was using the picture that I showed there, and I'm going to imagine that for some mean reason, she has leant back and put all her weight on the thin area of the heel. So the area of each heel is 2 centimeters squared. The Queen has 2 legs, and so therefore the overall area of just those thin points of stiletto is 4 centimeters squared. So you've got the data there to work this out. Put this into the equation. Tell me what you think the pressure is. I'm going to pause for 5 seconds. You can pause the video, and then I'll put the answer up in 5, 4, 3, 2, 1. So you should have put in 550 newtons divided by 4 centimeters. That's the force divided by the area. If you put that into the calculator, you get the number 137 newtons per centimeter squared. So the Queen Stilettos concentrates the force so that in each centimeter squared, there is a force of 137 newtons per centimeter squared. So that means that it should hurt much more to be stood on your foot in stilettos by the Queen than it would for an elephant, which is quite scary, I suppose. Now, they do ask lots of questions about pressure in the exam, and I want to kind of put in for you 3 little points and tips that are going to really help you with this. And there's 2 ways that they ask questions that seem to trip people up. The first is where it says state the relationship between pressure, force and area. And people look at that and think, well, I don't know, what am I supposed to write? All this question is asking for you to do is to write down the equation. So you'd put in your paper, pressure equals force divided by area. That's what that question is asking. And it's really easy to answer. It's the way they word it that sometimes tricks people. The second one, again, it's the wording that somehow tricks people up. It says show that question. Where they ask show that questions, what the examiner is looking for is for you to put all the information that is put there into the equation, and they give you the answer. And people don't quite realise that. So why have they bothered giving us the answer? Usually because they're going to use that answer in the next question. So the example I've put here is show that the pressure exerted on a ski of 20 centimetres squared is 50 newtons per centimetre squared if the skier weighs 1,000 newtons. So what they're asking you to do is to put the numbers in the equation, and they should balance out and equal out. So if I put here the pressure in the question was 50 newtons per centimetre squared, and that equals, we said force, which was 1,000 newtons, divided by 20 centimetres, which was the area. So if I do that in the calculator, 1,000 divided by 20 centimetres does equal 50. And so it shows that that is there. Be prepared to rearrange the equation. Pressure equals force divided by area. You would need to be able to rearrange the equation so you can work out the area using the pressure and the force. Use your basic algebra. If you want to move the area across, you times both sides by area to get rid of the area on one side, and so therefore you can move it across to the other. And so force would equal pressure times area. I'll do a video at some point on how to rearrange equations and how to do that. Now, pressure does not only exist on solids and on surfaces. Pressure also exists in gas and liquids. Now, to make you understand this, we need to understand a couple of simple things. First of which, that gases and liquids also have mass, and if they have mass, they also have weight. If I blow up a balloon, like I did in the lab earlier, then you would find that the difference between an unblown balloon and a blown up balloon is about 0.23 grams. This in turn means that that's being pulled down, and that would have a mass of 0.023 newtons. Now, that doesn't sound like much until you think about all of the air that is above you all pushing down on you. And so if you imagine there's a column of air above you right now, and that goes up 30 miles, and all of that air in that 30 miles is pushing down. Now, it does get thinner as it goes at the top, so it's not a standard amount of weight that goes up, but you can imagine that actually puts a lot more pressure on you. And in fact, if you stand at sea level, that pressure of that air is about 10 newtons per centimetre. So the air pushes on your skin with a force of 10 newtons for every centimetre squared. That's like having 100-gram mass on every centimetre of your skin pushed around. It's an incredible amount. Now, obviously, if you go up high, if you go to the top of Everest, there's less air on top of you, and so the pressure at the top of Mount Everest is much less. I want to show you the power of air pressure by you doing a simple experiment at home. So I'm going to go to my kitchen now, and we're going to video me showing you this practical. I want you to have a go at home and see if you can make it work. It'd be great if you can get yourself videoed, and then share with us the results that you get, and we'll see who gets the biggest result for using air pressure to do so. I'm not going to give it too much away because I want you to watch the next bit. So I'm going to stop the video there. You go and have a go at the practical, then come back onto the video, and I will do a summary at the end for how you've done. Okay, we're going to do an experiment to see if we can use air pressure to crush a can using a simple setup. We've got a cooker. You're going to need some heat-proof gloves, just some oven mitts. You're going to need a little bit of water, and you're going to need an empty can. You're also going to need a washing up bowl full of cold water. So this is what you do. You take your can and you fill with a little bit of water, not much, just enough really to cover the bottom. So I don't know if you can hear that, just a little bit, maybe a tiny bit more. So we just want to cover the bottom, enough to make a little bit of steam. So there we go. So that's probably filled up to about there. So about right to that level, about there. So not much at all. Then take your cooker and put your cooker on and leave it on full heat. We're going to heat it up as quick as we can. And you put your can on top of that. So whilst that's heating, we need to think about what's going to happen. So the water in the bottom, as it heats, is going to turn into steam. When it turns into steam, it's going to force the air out, and it's going to fill the inside of that with just steam. Once that's happened, I'm going to put this into the cold water over here, where all of that steam will turn back into water, and it'll leave me with a vacuum on the inside, which means the pressure of all the air on the outside will push in against the can. Now, it's going to take, I don't know, 4 or 5 minutes to reach the point where we start getting steam coming out. So I'm going to pause the video here. I'm going to put it back on when it's ready to go, and I'll show you what happens and what I need you to do. Okay, you can see now the steam is coming out. You can actually hear it boiling as well. So the can itself, I think, is about ready. So what we're going to do is we're going to take the gloves like this, Emily, there we go, gloves like this, and I'm going to make sure, now remember this is very hot. First job actually we're going to do is going to turn the cooker off, particularly if you've got gas, make sure all flames and heating is off before you then pick it up. You're going to take your heat-proof your heat-proof gloves, and you're going to put it, and you're going to try and put it around so that the hole is perpendicular with the gloves, and we're going to pick it up and we're going to dump it into the water, and it's got to be a quick dunk. Now your gloves are going to get wet, there's nothing much I could do about that, they will dry quickly. So here we go, take the can, put it in, tip it over, and there we go, and it's done it. So you can see, and again hopefully this will work with you. I will say, if your parents have got a bigger beer can, then it works better. So the bigger the can, the better it works. But you can see the air pressure has completely collapsed the can. And that was the air on the outside pushing in. And because we took out all of the particles on the inside, we made a vacuum, the force of the air on the outside was enough to slightly compress the can. Be great if you could take a video of you doing that and share it with us, and we'll see who was the best at making the compressed cans. So, well, I hope that worked. I hope that none of you have any injuries, and I hope that you've got some nicely compressed cans. So I want to quickly summarize all the elements of this video, and to do that, just going to quickly go through a couple of points. First of all, the definition: pressure is a force spread out over an area. We can put this into an equation, we can express it in an equation of pressure equals force divided by area. You will need to know that equation off by heart. Larger surface areas have lower pressures, smaller surface areas have higher pressures. So if I want something to go through something, I use a very small surface area. If I want something not to go through something, I use a very large surface area. And the surface area can change how that works. Also, remember that gas and liquids will also exert a pressure. Now, if you are looking for an extension, if you continue on with the video, there is an extension that I've put right at the end for those of you that really want to push yourself. For everyone else, thank you for watching, and I'll see you again soon. Here is the extension task, particularly for the scholars. What I've presented you here is a measuring cylinder, the measuring cylinder being a column, so it will have a surface area of a circle at the bottom, and then to find the volume you could times it by the height. In this measuring cylinder, it's filled up to the 50 milliliter mark, and the extra bit of information that you need for this is that 1 milliliter of water weighs 0.01 newtons. There is enough information in that question there for you to be able to tell me the pressure at the bottom of the water. That you can do, use the equation, make sure you can work out the force, make sure you can work out the area, and you'll be able to find out the pressure of the water at the bottom of the measuring cylinder. Thank you. Bye-bye.